Okay guys, in this video we're going to start talking about vectors. This is, maybe I should note here in your book, this is chapter 3 in your text, which is about vectors. First we're going to talk a little bit about vectors in 2 dimensions, which will be familiar from previous courses, and then we're going to move on to talking about vectors in 3 dimensions. So first of all, just so we're clear on the definition of what a vector is, this is a measurement that has both a size or a magnitude and direction. So by magnitude, of course, we're meaning that this is some sort of a measurement with a number value. So this is going to be some sort of a number with a unit. And the direction, of course, well, I think that's self-explanatory. You know what that means. So we have a variety of different vector measurements. So our examples for vectors: displacement is a vector, velocity is a vector, acceleration is a vector, etc. These are vectors are as opposed to scalars, right? So the opposite of a vector would be a scalar quantity. I'll write that up here, scalar. So scalar quantities are quantities that have no direction. So we're going to be discussing vectors, not scalars at the moment. So let's first of all start off by reviewing some material that should be familiar to you, and that is combining or adding vectors. So adding vectors. And we have 2 basic ways of adding vectors. We can do it geometrically and we can do it algebraically. So let's just remember to do this geometrically, involves taking the 2 vectors and sort of measuring them to some length scale where the length of the vector arrow indicates the magnitude, and then combining the vectors tip to tail. So what do I mean by that? Well, let's imagine we have 3 vectors. We could have maybe, let's say this is vector A, and what you're going to see me do is when I have a vector, any vector quantity, when I write the vector, I'm going to put a little arrow above, and this arrow indicates that the quantity is a vector. So if I have vector A, and then maybe there's another vector here, let's call that vector B, and then maybe I have a third vector here, this is vector C. Now we could, if these were our 3 vectors and we put them in this fashion, tip to tail, we could then go ahead and measure their or determine their sums geometrically. So for instance, A plus B would be, well, if this is where A starts and this is where B ends, then this vector, we'll just do a solid line, that vector right there, this would be A plus B. And if you wanted to do all 3 of them, A plus B plus C, then that would be, here's where A starts, here's where C ends. So this here would be A plus B plus C. You could see, of course, we could keep going, and you could even do B plus C. Well, here's where B starts and here's where C ends, so you could actually go ahead and put in B plus C. Okay, so that's basic geometric addition of vectors. It might be worth making a little note too. You could subtract vectors. So I'll just put a little aside right here. What if you had, let's say this is A, and let's say that B looks like, I don't know, let's say B looks like this. Well, based on what we just said, then we could say that this, start to finish, this would be A plus B. But what if I asked you, what if the question was, what's A minus B? In other words, what if I took A, what if I was subtracting vector B away from A? And the way we would do that is we would take vector B and rotate him 180 degrees. So now this would be, this is the vector minus B. It's the exact opposite, the anti-parallel vector. Same length, same magnitude, but exactly opposite direction. In other words, this now here's where A begins, here's where minus B ends. So if I were to draw that line, this would be then A plus minus B. See, this is minus B, so I took A plus minus B. Of course, that's the same thing as A minus B. So really quickly, that's how you would then, if you were asked to geometrically subtract vectors, that's how that works. I think that's fairly self-explanatory. Now, this is a really clunky, kind of annoying, labor-intensive way to combine vectors. So usually the way we do this is algebraically. So let's remember how we algebraically combine vectors. So let's imagine I've got a, let's go ahead and put in some axes. So here's a y-axis, and here's an x-axis here. And what if I had a couple of vectors? Actually, you know what I'm going to do? To remember this little bit of vector operation, I'm just going to imagine one vector. What if I had a vector here, and I don't know, we could call this vector right here. Let's call that vector S. This is vector S right here. One way to think about vector S is to go ahead and take vector S and split him into components. So hopefully that's a word that you remember from previous physics class. In other words, there's a component of S, there's a piece of S here. Maybe I'll go a little bit bigger so you can see this. There's going to be a piece of S lying along the x-axis, and there's going to be a piece of S lying along the y-axis, like that. In other words, this right here, this is S sub x, and this component right here, this is S sub y. And these are what we call the components of vector S. So here's S, and these are the components. And you can see, I eyeballed this, it might not be exact, but what I'm imagining is if I started here and drew a line up perpendicular to the x-axis and a line over here perpendicular to the y-axis, that's how I know where to end my arrow. So in fact, it looks like maybe this vector I made a little bit too long, but I think you get the idea. So these are the components, and we're going to see that components are helpful if you want to combine vectors algebraically. So the question then is, how do I figure out the magnitudes of these components? I know the directions along the x-axis and y-axis, but how could I figure out how big they are? Well, to do that, I need to know an angle. And so I'm going to give you an angle, and let's say that this angle right here, that angle, let's call it theta. And let's imagine that this angle, if I want to know this angle right here, I'm just going to give it to you. I'm going to say that that angle is a 45-degree angle. And so now what I've got here is a right triangle. You can see that this is going to be a right triangle. And I can go ahead and I can determine the components using my trig functions. So we remember so, ka, toa. This should be familiar. So I can say that S sub x now is going to be equal to S, the magnitude of S, times the cosine of this angle 45. But I've got to be careful here because the 45 degrees is negative. The reason it's negative, if you can remember this from previous classes, clockwise we always establish as the positive direction, and counterclockwise is the negative direction. Oop, I screwed that up. Counterclockwise is the negative direction. Clockwise is the negative direction. Counterclockwise is the positive direction. Sorry. So that's correct now. In other words, if I start from the x-axis, which is my reference line, and I go down, in other words, if I go clockwise 45 degrees, that means that this is negative. In other words, now I can say that this component here is S cosine negative 45 degrees. Similarly, if I wanted to know S sub y, I'm going to use the sine, so I'm going to say S times the sine of negative 45. Okay, so you got to include that negative. then the negative 45 isn't going to matter for the cosine, because the cosine of positive 45 and negative 45 is exactly the same number. But with the sine, by taking the sine of negative 45, I'm going to get a negative value, which is important because the y component of s is a negative y value. So that negative 45 is important. I should note you could have called theta positive 360 minus 45, or positive 315 degrees. Negative 45, positive 315, these are identical angles. In other words, I could have called theta this angle here as well. This could have been theta as well. That's positive 315 as opposed to negative 45. Get the same values either way. So that's a little bit about splitting up a vector into components. And before I get to how this is going to help me add vectors, let's just let's go ahead and remember some other things. What if I wanted to go backwards? What if I wanted to take the y component and the x component and combine them to get the original vector? How could I do that? Well, if it's a right triangle, then I can use the Pythagorean theorem. In other words, I can say that s then is equal to the square root of sy squared plus s sub x squared. In other words, c equals the square root of a squared plus b squared. Right? That's what I'm saying. C, this is the hypotenuse of the right triangle, is equal to the square root of a squared plus b squared. So I can indicate, I can sort of go backwards by saying the vector, the original vector, in this case we're calling it s, is equal to the square root of its components squared. That's an important sort of general relationship that you'll see frequently used. And then I could go back, by the way, and get the angle as well. What if I was curious to find this angle? What if I didn't know that that was a 45-degree angle? How could I find it from x and s? Well, I can use the tangent of the angle. And I could say that the tangent of that angle, theta, tangent is opposite over adjacent. So that's going to be s sub y over s sub x. And that's another relationship that is frequently used. So I'll put a box around it so that we can remember that relationship. And then you could, of course, go to the next step and say that theta equals the arctangent. I'm going to move that so that you can see all of it. The next step from this would then be to say theta equals the arctangent of sy over sx. Okay, so frequently some useful relationships. All right, I think that's where I'm going to stop for now. So we've discussed adding vectors geometrically, and now we've talked about breaking a vector into its components. So this was, I'm actually going to throw a little vocab word at you. I didn't really label this, but this is splitting a vector into components. This is what we call vector resolution, or resolving a vector into its components. So that's it for now. In the next video, we're going to talk about combining vectors algebraically. We're going to use vector resolution to combine vectors algebraically, and we're going to see that's really helpful, particularly when we're in 3 dimensions. So we go 3D next unit.